The second kind of elimination reaction that alkyl halides can undergo is an E1 elimination reaction. E stands for elimination and 1 stands for unimolecular, which means there is only one species which is going to take part in the rate determining step. And that one species is the alkyl halide. So the rate here is proportional to the alkyl halide. As you change the concentration of the alkyl halide, the rate is going to change. So because we know that only the alkyl halide takes part in the rate determining step of the reaction, an E1 elimination reaction must have at least two steps. Here is the representation of an E1 elimination reaction, and the product is again an alkene. Let's go on to the mechanism for the E1 elimination reaction. The E1 elimination reaction happens in two steps. In the first step, the leaving group is going to leave, thereby forming the carbocation. And it is the slowest step, and this is the rate determining step. And this step is similar to what we have seen in the case of SN1 reaction, where the first step is also the formation of the carbocation. And once the carbocation is formed, it can abstract the beta hydrogen. Now, for this molecule right here, if you consider this as your alpha carbon, you have three beta carbons, and all of these three beta carbons are one and the same. So it doesn't really matter whether you abstract any one of these hydrogens. It's going to lead to exactly the same product. Okay, so once the carbocation is formed, the base comes and abstracts this hydrogen, thrusts these electrons to form a double bond to form the product alkene. And this is normally a fast step. So together, the first step is the formation of the carbocation, which is the slowest step, and therefore that is the rate determining step. And the second step is where the base comes and abstracts this hydrogen to form the final product. Now we might be thinking, how does a weak base such as water is able to go and remove a hydrogen from an sp3 carbon? So if you take a look into this is our sp3 carbon, and normally when you have an ethane molecule where you only have sp3 carbons, removing that hydrogen is going to be very, very tough because the pKa value of this compound is approximately 60. Right? So if that's going to be the case, how it's possible to remove this hydrogen? Now there are two main reasons for this. The first one is the pKa is greatly reduced because of the presence of the positive charge on the adjacent carbon. Take a look into this. This has a positive charge. This carbon right here has got a positive charge on it. Now when you remove this proton right here by using a base, this is going to leave behind some electrons. Some of these electrons will be accepted by this positively charged carbocation. And the second reason is hyperconjugation. Hyperconjugation is going to weaken the CH bond by draining electron density. Now, what is hyperconjugation? Hyperconjugation is a stabilization effect that is brought by the overlapping of the sigma orbital with that of the p orbital, where some of the electrons from the sigma orbital is going to move on to the empty p orbital. So the positive charge on this carbon can be greatly reduced. So if more and more electrons are going to be moving in this direction, this hydrogen can be easily lost. And therefore, it would be easy for even a weak base such as water to remove a hydrogen from the sp3 carbon. Just as we have seen in the case of E2 elimination reaction, the E1 reaction is also regioselective, in which case there is preferential formation of one particular regioisomer. So here is the tertiary alkyl halide. Let's look into the mechanism for this reaction and predict the products for this reaction. So to begin with, it's going to form the carbocation. So here in this case, it's going to form the tertiary carbocation. And in the next step, once this carbocation is formed, beta hydrogen will be abstracted. So here there are two different types of beta hydrogen, right? Abstracting any one of these beta hydrogens will lead to the product. But which one is the major product? Always the most substituted alkene is the major product. Now, between these two, which one is the major product? Obviously, this is going to be the major product since this is highly substituted, comparatively highly substituted, and therefore this is the most stable product. And the most stable alkene is obtained by removing a hydrogen from the beta carbon, which has fewest number of hydrogens. So this is the carbon which has fewest number of hydrogens, and this is a major compound, major alkene. Why is the most stable alkene formed as the major product? For that, we have to look into the reaction coordinate. This is our tertiary alkyl halide. So to begin with, it's going to first form the carbocation intermediate. So this is our carbocation intermediate, and here is the transition state for it. So they're going to have exactly for both of those reactions, they are going to be only one carbocation. Once that carbocation is formed, it's going to take two different pathways. Okay, one leading to the least substituted alkene, and the other one leading to the most substituted alkene. And as you can see from here, for the formation of the most substituted alkene, it leads through the most stable transition state. The transition state is lower in energy, and therefore this is going to be the major product. The most substituted product is going to be the major product. Just as we have seen in the case of SN1, SN2, and E2 reactions, here again the weakest base is going to be the best leaving group. So if you have an alkyl iodide and an alkyl fluoride, obviously the reaction with alkyl iodide is going to be faster because I minus is a better leaving group. In all of the reactions, whether it's substitution reaction or elimination reaction, we have to remove the halogen, right? We have to remove the halide ions. So since I minus is a weaker base, it is the best leaving group.